Today we are exploring Newton's second law, which is also known as the momentum principle. And this states that the change in momentum of a system is equal to the net force acting on that system multiplied by the duration of the interaction, also known as delta t. In order to test Newton's second law, I recorded a billiard ball traveling in an assumed one-dimensional direction with an assumed net force interacting on that system equal to 0. Based on my experimental video and the computational model that I created in Python, it was evident that given the assumptions, Newton's second law in the Python program did not accurately predict the motion of the billiard ball. To outline my report, I will now start by showing you the video I recorded. I will then explain the Python code I used to make a computational model, and then I will finish with the analysis of how the computational model compares to the observed motion of the billiard ball. Now here is the video being run in the tracker program. Whenever I back the video up, we can see the labeled axis and how it's centered on the center of mass of the ball. And then we can also see the blue calibration stick that are used to predict the distances within the video. Now let's say that we recorded a ball rolling down a ramp. In order to easily analyze this data, we could rotate the axis so that it would be parallel to the motion. Flipping the axis truly has no effect on the data that we analyze. It merely puts a different label on that data. We could use a three-dimensional vector with the x-axis pointing up, but it doesn't really matter. We just need to be explicit about our choice. With this one-dimensional motion that we see here, we just have to choose one axis that is parallel to the motion. For this case, the x-axis with the positive direction going this way, the direction of motion, is easiest for our analyzation. Now the origin was chosen as the center of the ball because it is very easy to track the movement of the ball when thinking about its center of mass. And we labeled the center of mass throughout the video to then see its motion. The positive direction was also chosen for the direction in which the ball is moving, because this is easier to analyze and we don't want to deal with negatives in our calculations. In this video we can also see that the time parameter runs from 840 frames to 880 frames. And this was set in order to capture the ball at the points when it is most likely to be moving at constant velocity. We did not want to start recording its motion as it was accelerating from the first of the pool cue. In order to make a computational model of the data, initial conditions such as the mass, position, and velocity were calculated. We can see these initial conditions here. For the model to work, I've manipulated sections of the code to contain fundamental principles such as the momentum principle. We can see these changes in the code here. We can run this module and see the predicted movement of the billiard ball. We can also make edits to the code by uncommenting certain lines, such as these here. And from this we can extract the data and put it into an Excel spreadsheet. And then we can create a graph such as this. Here we can see the comparison between the computational model and the observed position versus time of the billiard ball. The computational model overpredicts the actual position of the ball. One may ask what this means. This indicates that some outside force must have acted on the billiard ball in the negative x direction. We originally assumed that the net force on the billiard ball was 0, but in fact this is not the case. The comparison between the computational and observed models indicate this. There are two major forces at work that prevent the ball from continuing at constant velocity. These are friction and then drag from the air. One may ask, what if we in fact were able to calculate the friction and drag force and apply this to our computational model? Since we included Newton's second law in our Python code, by calculating the vector quantity of the net force, we could then have a model that nearly predicts the motion of our object to its true exact value. To summarize this experiment, we tested Newton's second law, which states that if the net force on an object is 0, then the velocity throughout that object's movement should be constant. Our observed model of the billiard ball's motion disagreed from the computational model based on Newton's second law. According to Newton's second law and our assumptions, the ball should have remained at constant velocity. The reason it did not is simply because we had too many assumptions in our experiment. We originally stated that the net force on the ball was 0, and that the ball moved in a one-dimensional direction. The net force on the ball was in fact not 0, and the ball also could have moved in more than one dimension that was not visible in the tracker analysis. These two assumptions caused our computational model in Python to disagree with our observed model.